I would also like to take this opportunity to express sincere thanks to Dynochem for providing this opportunity for me to share our work, and hopefully it will be a good learning experience for everyone to see what we have done. And essentially what I'm going to talk about is the model and experimental driven approach, essentially to develop a reaction model using the Dynochem platform, and how it was applied to both batch and continuous process development for Grignard reactions. And primarily this is important because Grignard reactions are very popular in pharmaceutical industries and other industries involving reaction engineering. So the outline of the presentation will be to discuss the background. Again, the main focus is going to be related to Grignard reaction chemistry with an emphasis on its operation in a continuous fashion. So using the first four experiments which I mentioned on the previous slide, the plot here shows on the y-axis concentration and on the x-axis time, and the solid lines are the model fit, and the empty dots and the square and the diamond are the actual experimental data obtained by IR. What we can see is that we have varied the equivalence of magnesium to benzyl bromide from almost 1.5 to 1 to 12 equivalents at different temperatures, and therefore this defined the parameter space for the model. Overall, the model fit looks really good. Moving on to the next set of experiments to confirm that we were indeed in the mass transfer free kinetics, we did this in a continuous operation at 400 RPM and 600 RPM, and what we see is indeed, based on the similarity of the two results with an experimental error, we were able to conclude that 400 RPM is indeed free of mass transfer, which is very good because most of our experiments were done at 400 RPM. This slide summarizes the estimates of the parameter with a 95% confidence interval, and the KR, which was modeled using Dynochem, assumes a reference temperature. In this case, we assumed a reference temperature of 0 degrees. As a true test to see how good the model fit was, we can use different criteria. And the criteria that I've used here is RMSE, which is the root mean square error. You can see that the RMSE for both benzyl bromide and Grignard, which were estimated separately, are very low and within 5 to 8%, therefore suggesting that the model is indeed a very good fit to the experimental data. And we were therefore able to use Dynochem and come up with a fit for use model, which is a very powerful platform because now we can actually, for the first time, capture the physical dynamics of the system, get a good estimate of the mass and energy balance. We can actually use the model without running another additional experiments to capture the effect of different magnesium supplies. We can also use the model to develop our regulatory submission packages specifically with regards to impurity controls, and also manufacturing benefits greatly from this model because we can use it to help guide operations and deviation planning and challenges like FMEA, magnesium recharge, and so on. Therefore, the goal was to share with you the innovative approach that we took to hopefully develop a satisfactory package which allows a robust process and justify the operation strategies for running this Grignard process from lab scale to commercial manufacturing.